Okay, this video is going to be over the most commonly missed problems from Registry Review Exam number 1. First video here is going to be about the first 10 or 11 problems, and then I will shoot a second video covering the others. This is to give you guys an idea as to how the approach for these problems should be taken in order to solve them. And should they get to the point where they maybe change up some numbers or things of that sort, that you would at least be able to go through and to identify what it is that you need to do in order to be able to solve it. So let's take a look at the first one. The first one here, the average photon beam energy produced by 6 MV linear accelerator is approximately what? If you look through some data or whatnot, or even if you look through other resources such as Khan or whatnot, the rule of thumb is that the average energy is 1/3 of the maximum energy. What they are giving you here is, of course, going to be the maximum energy. So because of that, what you will do is you will take this right here, you will take 6, cut it into a third. And so the average energy should be this. And it should work generally for just about any energy that you put in there. So the correct answer here is going to be 2. Okay, so let's move on to the next question. All right. The intensity of a radiation beam is measured at a distance of 100 and is found to be this. What is the intensity of the beam at 105? If you will remember, the intensity, the ratio of the intensities is going to be equal to the distances squared. If you put them, instead of having 1/2 over here, you'd have 2/1. So we don't know what the intensity here is of one of these, but we know what it is for the other. So we've got intensity of 1 is equal to d2 squared over d1 squared times intensity of 2. That's if you multiply both sides here by 2, because that cancels over here. And then if you want to solve for the intensity of 2, which we don't know, it's going to be equal to the intensity of 1 times d1 squared over d2 squared. This also follows the inverse square law. So in this particular case, we don't know what the intensity of 2 is. We know what the intensity of 1 is. It's 150 centigrade per minute multiplied by, now the second, this corresponds to this. So in this particular case, if we follow this formula here, we're going to have 100 cm. That ends up getting squared. And then the other is going to be 105 there. This should follow because the second intensity is further away from this one. And so when we go through and we square this, we should end up with a smaller number here. So that's also a clue. If you end up measuring at a further distance away, then you should end up with an intensity that's smaller than that. So let me see if I can get a calculator going here, which you have to stop this particular menu here in order to be able to access it. There we go. So if I take 100, you can square it or you can wait till later on, but I'll go ahead and square it now. Divided by 105 squared. But there we go. Okay, so that gets multiplied by 150. So we end up with 136. And that in fact ends up being the correct answer. So drawings here. All right, so let's go on to the third question. What is the approximate Dmax of a 10 MV linear accelerator? I have a copy of this in the second exam list of PowerPoints here, so you can go to it and you can grab it. As you see here, it is roughly, in case you forget, roughly here you're looking at E divided by 4. So your maximum energy divided by 4. So in this particular case, you're looking at 2.5. Okay, so that's question 3. Let's go on to question 4. Now, a lot of these questions are brought up at random if you were to go through these in this particular setup. So I'm just referring them to this way so I can keep track of it. What fraction would you multiply an electron energy by to estimate the 90% isodose range? 90% isodose range is going to be about 1/4. So that's something for you to remember. So that's question 4. Question 5. So this is a problem. A patient, and I've got a mock problems, something very similar to this. But let's go ahead and let's go through this because I think this is worthwhile. A patient is to receive 300 centigrade per day on a cobalt-60 unit through a single posterior field. The dose rate in air at 80 cm is 105.3 centigrade per minute, and the backscatter factor is 1.029. Percent depth dose is 87.5%. So let's find the treatment time. Now, let's sort of chart all of this out because otherwise it gets to be a little confusing. Remember here that the whole reason that we have a backscatter factor is that we're trying to figure out how to be able to correlate dose in air to the same point here in a phantom at the depth of maximum dose. So we've got a small little buildup region around this in air. This is independent of the PDD. So the backscatter factor helps us get from air into the maximum depth in the patient. PDD is going to help us get from here down to here to some other depth beyond this. So in order for us to be able to figure out exactly what the time needs to be, we're going to use formula dose is equal to, and then we've got the dose rate times the backscatter factor times the PDD. So in this particular case, we're going to take 300 centigrade and we're going to divide it by 105.3 centigrade per minute. That is going to be multiplied by 1.029. And we're going to change this 87.5% to a decimal. So it'll be 0.875. So when we multiply all of that out, what do we come up with? Let's see, let's clear everything out. So I'm going to take, I'm going to come up with a number down here at the bottom first, 105.3 multiplied by 1.029 multiplied by 0.875. It's equal to this. I'm going to take the reciprocal of it and then multiply it by 300. And so we come up with 3.16. So what I'm going to do is I'm going to say that this is, okay, this is going to be 3.16 minutes. So we can see here already that that's going to rule this out. It's also going to rule this out. The question is, which one of these is it going to be closer to? Well, if I've got 3.16 minutes, how do I figure out how many seconds that is? Well, if I strip off the number of minutes, which is basically subtracting the number that's to the left of the decimal point here, and multiply by 60, that should tell me 9.85. So if I look at this, that's or 3 minutes and 9.85 seconds rounds to 10 seconds. So now we can see why this is the answer here. Okay, so that was 1, 2, 3, 4, question 5. Okay, patient is usually treated at 100 SSD. Patient must be treated on a stretcher at 135 SSD. So for the tumor dose and size treatment area to remain the same as originally planned, which of the following statements is true? So let's draw a model here of what's going on. So we've got, originally we had our patient here, and it had a certain field size here, and that was being treated at 100 SSD. So now, for logistical reasons and whatever else, we want to treat the same volume here, but we're going to treat this at 135 SSD. In order for us to be able to make sure that we are treating the same area there, all of these things are going to have to are going to end up happening. What's going to happen is, in order for us to make sure that we hit the same volume, is that we're going to tighten down on the collimator. Collimator setting is going to decrease because as we are moving the patient further out, if we leave the collimator heading the same, then what happens is whatever we treat here at 100, whatever distance we end up treating here at 100 is going to end up being significantly bigger, plus whatever. So that's going to be bigger. In order for us to make sure that we just want to hit that same distance there at 135, we're going to have to shorten or bring in the collimator edges here. Otherwise, we end up treating more than what we want. So that's why number 1 is true. Number 2, why would the monitor unit setting increase? Why would we have more monitor units here? Well, what other effect is going on here? As we're going from 100 to 135, what's happening to the intensity of the dose? The intensity at 135 is going to be significantly less than the intensity at 100 because it's further away. It's the inverse square law. In order for us to be able to make sure that we're delivering the dose here that we were here, how do we increase that? We increase that by increasing the number of monitor units. And the third thing here is that the exit dose will slightly increase. This one may not be easy to see because the PDD here at one distance, say 100, is going to have a certain characteristic. It's going to fall off to a certain level here. And what you see out here is certainly going to be smaller than what you see here. The further away that this phantom is, and at this point it is at 135, what you're going to see is that the PDD, the exit dose, what you see down here, is actually going to increase slightly, because when this PDD increases, or when this SSD increases, the PDD also increases as well. In other words, the stuff that's downstream, you're going to see less of a fall off than what you would here. So that's why the exit dose will slightly increase, is because the PDD is going to be a little bit higher at a greater distance away than what you see here. That's why all three of those are in fact true. You can see here, it's marked that way. Okay, so 1, 2, 3, 4, 5, 6. Backscatter factors. Backscatter factors are independent of SSD. That's why we have them. This was a step getting us towards the tissue error ratio, eventually the tissue maximum ratio. It is in fact dependent on the field size. It is dependent on the type of beam you're using, and it is dependent on the TAR. One thing it is not, one thing it was designed to do is to get rid of the SSD requirement. So patient was mistakenly treated at 90 cm SSD instead of 100 due to a misaligned ODI. So the prescribed dose was 2.5 gray. What did the patient actually receive? The patient actually received, since they're at 90 as opposed to 100, what do you think might have happened? Do you think they would have gotten less or more? In this particular case, they would end up with more. Question is how much? In order to be able to do that, again, we are going to be looking at the inverse square law. So the dose here at 90 is going to end up being the dose delivered, or that should have been delivered at 100 times 100 divided by 90, and that is going to end up getting squared. So the dose at 90 is going to equal 2.5 gray times this result. It's going to be 1.23. And the dose here at 90 is going to end up being, when that's multiplied by 2.5, it ends up being 3.09 gray. That's the answer. So treatment time of 2.0 minutes requires that you add a wedge with a factor. A treatment time of 2.0 minutes requires that you add a wedge factor with this. What would be the new treatment? That's a weird way to write the question, but let's say you've got something that requires a treatment time of 2 minutes and you have to add a wedge in that has a factor of 0.5. What's going to be the new treatment time? This is something we haven't specifically gone over just yet, but if you do have to add in a wedge factor for something like that, basically you're going to be dividing the amount of time by that factor. So in this particular case, you've got 2.0 minutes. You're going to divide that by 0.5, and so you end up with 4.0 minutes. So that'll be your answer there. All right. Find the equivalent square of a resultant field of a 12 by 12 field with a 4 by 6 block. This one I can understand might cause problems. So if you have, and it doesn't matter what the shape of this is, it doesn't matter where it is or whatever else. If you have, I'm just going to take the field area is going to be equal to 12 by 12, which is 144. And it doesn't give a unit here, so it doesn't really matter, but I'm gonna say centimeters. The blocked area is going to be equal to 4 by 6. Now, whatever the units are up here, I'm going to make them the same down here. If you multiply those two numbers together, as I did up here, you end up with 24 cm squared. If you take the difference, then you come up with 120 cm squared. This is how much unblocked area that you have. In order to figure out if you want to be able to find out what sort of an equivalent square that happens to be, you take 120 centimeters cubed, you take the square root of it. When you do that, you come up with 10.95. And when rounded, it's a square field of 11 by 11. So that's where that comes from. Okay, so this will be the last problem out of this particular video. And again, I will create another one in order to be able to kind of show you how the others are worked. So a patient is 20 cm thick. You are to give 3000 centigrade to the midline, weighted 2 to 1, right to left. The percentage depth dose for a depth of 10 cm is 0.641. So what is the given dose on the left side? This is something to watch for. Watch the wording on this. So the dose that you're going to deliver to midline is going to be 3000. So you're delivering 3000 centigrade. Since you're delivering it to midline and the patient is 20 cm thick, the depth being 10 cm is 0.641. So you take that, and assuming no other modifiers here, you take that. And so how much is actually being delivered? Well, take 3000, divide it by 0.641. And so you come up with 4,680, 80.18 centigrade. Now, since the weighting here is 2 to 1 right to left, that means coming in from the right side of the patient, it's twice what you would get coming in from the left side. So in other words, the weighting 2 to 1, you add up all of the weightings and you come up with 3. That means on the left side here is going to have 1/3 of the weighting. The right side is going to have 2/3 of the weighting. That also means 1/3 of the dose is coming through on the left side, whereas 2/3 of the dose is coming in on the right side. That should lead you to conclude that if I take the total amount of dose being delivered and essentially end up multiplying that by 1/3 or dividing by 3, depending on how you want to write that. So if I take this and divide it by 3, then you come up with 1,560 centigrade. And that's exactly what the answer is. So I hope going through a lot of these problems here has kind of helped you. Again, I will be putting out the second part to this.